final lesson for Unit 6 is to talk about velocity as a vector. And velocity as a vector is a really interesting and useful concept. I'm going to try to demonstrate it to you using this information here, the idea of your heading, which is to say where you're pointing and how fast you're moving, and then the speed of the medium that you are in, so like the wind if you're flying, or the water, the current if you're in the water, and then the idea of the bearing being what way you actually go. So I've just made up a little demonstration here where I have an airplane, which is this little A, and the airplane is pointed in the direction of vector A and traveling with that, what we call airspeed. I have another vector over here, which is the wind. And let's just make the wind point downward for a sec. So my plane is pointing this way, and I'm flying this way. But my plane, when I actually travel, doesn't go that way, right? It actually goes, you can see the trace here, the path it takes is actually this way. So if what you were hoping was to kind of land somewhere over here, right, then not taking the wind into account is causing you to fly, directly off course, right? You're going to miss your destination by a great deal. Now, the idea behind this, to understand, let's have the wind point a different way now. This time when I move, right, again, my plane is pointed in the direction of A, but the wind is causing me to, move at an entirely different direction than I thought, right? So a lot of this unit is kind of the idea of this problem. I'm an aircraft, I have a certain airspeed, the wind is blowing in a certain direction, and I have a destination. Like, let's say my destination is over here, right? That's where I actually want to get. And let's say the wind is doing this. How do I orient the plane so that it actually goes where I want it, right? You can see right now my plane vector is too tall, right? Let's reduce let's aim it closer to the x-axis, and you can see I can actually get a bit closer. Actually, probably going to aim underneath the x-axis. So underneath the x-axis is a little bit too low now. So maybe I'll just aim directly east. And you can see if I aim directly east, right, I'm actually going to reach my target. Now, that's not that intuitive, right? Like think about these two vectors for a second. A is pointing straight to the east. W is pointing, north and to the west. And only by doing exactly that can I make sure that my plane actually goes where I intend it to go, right? And so this is kind of the concept that today's lesson is about, and the type of problem that you're going to solve. You want to make the resultant, right, point in the correct direction so that you reach the destination, right? In many of the problems that we get. But the bigger thing to understand is simply the idea that the way you are facing is not where you are actually going to go. And if any of you have swam across a lake or swam a considerable distance in waves, you'll know that you're kind of constantly adjusting the way that you're pointing. If you just sort of set your sight on the other side of the water and swim in that exact direction, you're going to end up way downstream, right? Like you need to use up some of your velocity to fight the current so that your actual resultant goes in the direction you intend to go. So one more time. A is the direction my plane is pointing, and the way my plane is attempting to move. W is the way the wind is blowing, and the combination of those two things result in how my plane actually travels. Okay? So it's pointed to the right, but it's actually traveling a little bit up and right, as a result of the wind. So this, just to understand the terms, okay, what we say is that the plane's speed relative to the air is its air velocity. So that would be the speed that it shows, on my plane. It says I'm going 800 kilometers an hour. That's my air velocity. the wind is the speed of the wind, and the ground velocity is how the plane is moving actually relative to the ground, which is kind of like, you can kind of think of this as like where you're actually going, which is the resultant. Okay, again, the equation is very simple. The resultant, the ground speed, is simply equal to the air speed plus the wind speed. I shouldn't say speed, I should say velocity, sorry, because speed is not a vector, velocity is a vector. So the ground velocity is equal to the air velocity plus the wind velocity. Okay? This gives you the idea of relative velocity, which is how, if a friend is walking away from you at 1 meter per second, are they moving at 1 meter per second east relative to you, or are you moving at 1 meter per second west relative to them? Right? There is actually no answer to that question. Both are legitimate ways of looking at what's happening. So how you're moving depends on what's called your frame of reference. And it's a good example here, because how you're moving relative to the air is like this, except the air itself is moving, so how you're moving relative to the ground is like this, right? They're different. So imagine you're in a car and you're traveling 100 kilometers an hour, right? And you're traveling west. And you pass a bus traveling 80 kilometers an hour west. Okay? What does the car appear to be doing to the bus? If you're sitting on the bus, you'll be watching that car pass you at a speed of 20 kilometers per hour. And because that's its relative speed relative to you, right? And this is kind of the idea. You take the velocity of A relative to the velocity B is simply velocity A minus velocity B. So the car relative to the bus, right, would be the car's velocity, 100 kilometers east or west, subtract the bus's velocity, 80 kilometers west. The result is 20 kilometers west. So to someone sitting on the bus, the car would be passing you at 20 kilometers an hour west, right? Now, on the other hand, to someone sitting on the bus, how quickly would that truck be approaching you? The truck is traveling 90, but you are traveling 80 towards the truck. So the truck appears to be coming at you at 170, right? This is why traffic coming at you always seems to be traveling much more rapidly than traffic around you, right? It's just a trick of assuming that you're not moving. Okay, so to someone sitting on the bus, the car would be passing at 20 kilometers an hour west. We say the relative velocity is 20 kilometers an hour west. Okay, the velocity of the truck relative to the car. So if you're in the car, you're going 100. The truck's coming at you at 90. The truck appears to be traveling at 190 kilometers an hour, right? If you were standing still and the truck was coming at 190, it would look the same as if you were in the car going 100 and the truck was coming at you at 90. Okay? Find the velocity of the bus relative to the velocity of the car. Okay, so what we're looking for here is the v of the car. The bus. I just mixed it up. Minus the velocity of the car. So v vec car. And how do you actually subtract these two vectors? Since they're in the same direction, you can just subtract their magnitudes, because remember, when two vectors are pointed in the same way, you can just, when they're parallel, you can just add or subtract their magnitudes as needed. So we have 80 west, take away 100 west. Well, what if I said, instead of negative 100 west, I said 80 west plus 100 east. The result would be 20 east. And that is what would be happening. If you were sitting in the car, the bus would actually appear to be traveling in the other direction, right? You're both going west, but since you are catching up to the bus, if you imagine yourself as standing still, the equivalent would be the bus coming towards you. And so we say the bus relative to the car has a velocity of 20 kilometers per hour in the east direction, which is kind of interesting because the bus is not actually going east, right? Relative to the ground. Relative to the car, it is going east. Okay? Note that the relative velocity of two objects does not depend on their position. So that's fine. It has nothing to do with where the objects are. It's just how they're moving. Okay, so this is just a review of how to do a quadrant bearing. So 15 degrees west of north, you would say north 15 degrees west, right? You start at north and you go 15 degrees towards west. So again, it's helpful to identify angles whose directions are given. Again, like I said yesterday, draw little axes, okay, around every corner of your angle, and it'll help you like sort of break it down into easier steps. Okay. Let's try this first one. So it says a plane is steering north 45 east with an airspeed of 525. The wind is from north 60 west at 98 kilometers an hour. What way would the plane actually be going, and at what speed? Okay. So again, let's use the vector addition app to just get the answer so we can picture it, and then we'll work through how you would do it. So according to the question, right? I'm just going to go back to my vector addition app here. My plane is traveling 525, so I'm going to set A equal to 5.25, and the plane is traveling north 45 east, which is equivalent to a true bearing of simply 45. Okay, so there's the plane in vector A. Now vector B is 98 kilometers an hour, but since I divided by 100 to get A, I got to divide by 100 to get B. So B is 0.98. Okay, and we'll just set this bearing back to 45. Okay, so and B, now this is another thing that's a little bit tricky about this. It says the wind is from north 60 west. Okay, from north 60 west. So if you draw the wind going north, so here's north, we'll drop it down by 60 to get to 300. There's north 60 west, right? But it said the wind is coming from that direction, not in that direction. So I'm going to take this, I'm going to rotate it 180 so that it's actually pointing down this way. When you draw it, you can just draw it like this, but draw the arrow pointed towards the center, and then you'll actually be able to finish your triangle anyway. Anyway, for me, the wind needs to be coming from this direction, so I'm going to move it by 180. I'm going to change 300 down to 120. Okay, and now I have the wind blowing from north 60 west. It's blowing from that direction. If I check the resultant here, right, I can see the plane is going to travel in a northeast direction, although it's going to be more east than they think and less north than they think. Okay, the plane is going to be traveling at 558 kilometers per hour, so it's actually going to be moving faster than the instruments say, right? The airspeed would say. And it's going to be traveling at a true bearing of 54.76, or you could say north 54.759 towards east, right? Would be where this green one is headed. Okay, so once again, let's go through this and we'll just draw it. I'm going to try and sort of freehand draw it the way that I would draw it if I was on the board. And what would it look like? So I would draw the plane traveling off at a 45-degree angle, and I would just, we'll just write down beside it 525 kilometers per hour. Okay. Okay, now the wind is from north 60 west. So how would I draw that on the board? I would draw here's north 60 west. So again, it's really helpful to draw a little axis. So let's draw a little axis here. So it's just a segment. Just draw a little axis. Okay, now the angle that I was talking about when I said 60 is right here. Okay, that little angle there is 60 degrees. Let's just get rid of some of this external information, and F we don't need either. Okay, so the 60 degrees, right, it would be right here, this little angle. Now, of course, if I measure this angle in GeoGebra, it's going to sorry, just measure the angle. if I actually measure the angle to label it, I'm not going to be able to get this right exactly as 60, right? I mean, it's going to be, I guess I could actually, if I rotate D 60, yeah, so C equals. Okay, so now I've got it to be exactly 60, but whatever. Okay, so the north 60 west is over here, but remember, this is the direction the wind is coming from. So if you actually want to draw the wind vector, what I suggest you do is just draw it pointed towards the middle, right? And this, let's rename this to W, and let's hide that one. Or sorry, hide that one. The wind, okay, is pointed in towards the center. The angle here between, so let's go angle DAB, no, BAD, is 45, right? So again, my little axis, I can draw that angle and I can see that. Yikes, what just happened to my, okay, there we go. Okay, 45. Now this D point again is nothing, it's just something I drew, so we can get rid of it. Now if I draw the wind coming towards the center, and then draw the plane going away from the center, then I can easily get the ground speed by simply doing C to B. This will be the way the plane actually travels. Now, may not be the best idea to do it that way, because I need to do a, I need to get its angle when I'm done. So maybe what I'm going to do instead is I'll draw the wind vector going down in this direction. So let's just do, let's just draw vector W. Vector A and A plus W. Okay, so there's the wind vector. I just shifted it down here. Remember, it's up to you where you want the vectors to start and finish. What's not up to you is how long they are and what way they point. But I didn't change that. It's the same direction it used to be pointing, and it's the same length. So now what I'm going to do is I'm going to do vector addition, right? To do vector addition, I need to complete the parallelogram, and then I need to find what's going across the side. Okay, so I'm going to make a little label here that says 98 kilometers per hour, and that is what the wind is doing. Now again, if you wanted to add this vector, which I'm just going to quickly rename to the A for airspeed. So I have the airspeed vector, I have the wind vector, okay, and I need to add them together. Let's hide that one since we don't need it anymore. Right. Oh yeah. Well, you know what? I actually do think I need that still, so let's leave it. Okay. Now I needed to know where this is. So let's draw a vector from point A plus W to A plus W plus A. Okay. So there's the like parallelogram. If I follow the wind first and then follow the plane, I'm going to end up here. Now I'm going to put this one in dotted just because it's only part of my parallelogram. It's not really a new vector, right? So to go across this thing, so airspeed plus wind speed. Okay, I get that. My resultant now is simply connects A to J. So there's the resultant, and we'll just rename this to vector G, which we're going to call its ground speed. Okay. Now all you're trying to do in this question is answer how long is G and what angle is it at. Now that can be a bit tricky, so let's zoom in a little bit over here and look at what we know about the angle. What do we actually know about the angle? Okay, you gotta think now. If I think of the angle between my original airspeed and my x-axis, then I know that I have a 45 degrees. I have 45 degrees here. Let's just hide this for a sec. And let me draw it here. So what would it be? Angle 0, sorry, from 10 to 00 to B. Okay, so look at the angle I just drew. You can't really zoom into it. So this is like drawing these things a bit careful, right? Because you've got a different vector in the middle of it. I'm not trying to capture the angle between my resultant. I just want the angle between my original vector, right? The airspeed, which will just quickly change to be in red, let's say. So I want the angle between the x-axis and the red. Now I also know that the angle down here, right, between the let's make this one blue, between the y-axis and the blue is 60 degrees, right? Because the same 60 that was up here is now down here, which means the little angle in the middle is 30 degrees, right? So the angle that's sort of inside my triangle is 75 degrees, right? To go all the way from the red down to the blue is 75 degrees. Now that I know that, okay, I can actually do the cosine law or what do I do here? No, I guess sorry, that's not really what I want to do. I want to just give me sorry. Right. Okay. Just lost my train of thought for a sec. Okay. So 75 degrees. So let's hide the 45 and we'll hide the angle so we know what we're talking about now. So I want the angle between W and A. Okay? And that's where the 75 degrees is coming from and how I got it. Okay? So for a moment, let's just hide the ground speed for a sec. Okay? And maybe let's get rid of these axes now that I don't really need them anymore. Well, actually, you know what? Now I'll keep them. Okay, so 75 degrees is in this corner. Now think about a parallelogram for a second. In a parallelogram, this corner's angle must be the same as this corner's angle. So again, let's just measure that quickly, and we'll go angle between and I'm really having a tough time drawing my angles today. Okay, notice that the angle on the opposite corner of the parallelogram has to be the same. Okay, so that means that if those two angles are the same, and the whole shape has to add up to 180, then the other two angles must be 105. You'd think like I would at least get it right half the time, since it's a 50-50 chance. But it's like I just... Okay, so look at my parallelogram. 105 at the top, right? 105 at the bottom, and then 75 in the corners. Now the 75 I actually don't really care about. It's the 105 I want. Because look at my triangle now. My triangle has one side is 98, the middle angle is 105, and the other side is 525. So I can finally solve this question with the cosine law. The airspeed is 525, the wind speed is 98, and the theta, between the two vectors, right, is 105 degrees. And now that I have that information, I'm good to go ahead and do the cosine law. So let's get rid of the grid here. And I mean, this is, I'll maybe shrink the diagram down a little so that, well, I was going to say I'm going to try to shrink it down a little. Okay, so I did want this to be at 45. So again, I know it's not the clearest diagram, but hopefully you're able to draw it, more clearly. So here is everything we know. Let's take it back to our page and we'll type out our answer now. Okay, so based on what we know, we are looking for the ground speed. So let's call it g is equal to, and the formula is really easy, right? So it's just airspeed plus wind speed. Okay. How do you actually add two vectors together, though? We know that we can do that. We can get the magnitude. Okay. The magnitude of g, we know, right, to square would be equal to, I'm just going to copy paste that probably faster than typing it out every time. So to get the magnitude, we would square the two kidding me? Okay. I was going to say, do I have to? Okay, we square those two, and then we do the cosine law to AB cos theta. Right, Word can't do a quick theta, or at least I don't know how to do it. Okay, now this is not vector V, this is, let's call A just to be consistent, and that could be W. Alright, there you go. So the magnitude of G is going to be A squared plus W squared minus 2AW cos theta. So what do we get here? We get 525 squared plus 98 squared minus 2 times 525 times 98 times cos 105. And that is equal to, just use GeoGebra to calculate this quickly, so 525 squared plus 98 squared minus 2 times 525 times 98 times cos 105 degrees gives me 311,861.48. Okay, and of course that number makes no sense because this plane is not traveling at 300,000 kilometers an hour. Reminds me that the other side of my equation was the magnitude of the ground speed squared, right? It's 311,861.48. So magnitude of g is just the square root of that. So let's take the square root b, oops. And we get 558.45. Now, this is consistent with what my program said it should be. You know, like what the vector addition app said, right? 558.4. Now, and though you might think the rounding's off, but the next number is a 4.6, so that's why I didn't round it up to 0.5. The last thing we need to do is we need to find the angle that this is going at. Okay? Now, again, what is kind of tricky about this is you have to have a good diagram to get this angle right. How could we get this angle? Either we would need to know the little angle between red and black, right? And then we could say that it's 75. We know this is 75. We could subtract it, right? Or we need to know the angle between blue and black. So we need to get one of those two in order to solve this. Let's work with blue and black since that's kind of in the triangle that we were working with. So I'm going to write underneath, use the sine law to find the bearing of the ground speed, or ground velocity. Okay, so in my triangle, I know that sine of, let's just call it, let's call it g, I guess, since, well, no, actually, that's not a good idea. Sine of, let's call it a. Okay, would be a sine of a divided by the airspeed, right, would be equal to sine of g divided by the ground speed. Okay, and so, let's just quickly have GeoGebra do that. So we know sine g, or we know g is, sorry, let me just type it out again, I guess. G is the angle opposite the ground speed, which is 105. And so let's just solve this one. So sine A equals 525 over 558.45 times sine 105 degrees. And that is equal to, so 525 over c times sine 105. And then inverse sine of that is 65.241 degrees. Okay, now what is this thing we just found? This thing we just found is the angle in the middle here. So let me measure it. Okay, I'm going to hide the other one, so we don't need that one anymore. So the angle I just found, right, would be the angle there. Now it's wrong because Is it wrong because my diagram is not right? Don't think so, because it should be... Let me pause, I'll figure this out. Okay, it turns out I just made a typo when I did arc sine. So when you do arc sine here, so inverse sine, it gives me 1.139. That of course is giving that in radians. So let's take theta and multiply by 180 divided by pi to convert it back to degrees. I guess I haven't fixed my problem because it's still wrong. I'll be back. Okay, probably this is the error. I think when it probably interpreted that as multiplication and not division. Okay, yeah, the math was right. The drawing, you gotta be careful when you mix and match using GeoGebra to draw it accurately versus sketching it. So the math we did was right. I just assumed that it would have the same angle because I had all the other angles right, but of course that's wrong because the length of the two vectors was off. So now that I can, like, let's just see if I can, now that I can sort of, let's just get rid of this. Don't need that one anymore. If you actually zoom this out, and you actually, if you actually draw it to the correct scale, which probably should have just done in the first place, you get 65.24081 in that internal thing, which is what we said, right? So how does that help us answer the question? Now, the angle that we just found, right, this one here, and again, let's get rid of angle alpha because we don't need that anymore. Don't really need this or that anymore either. Okay, the angle that we just found is the angle in between the black vector and the blue vector. So you can kind of think of this as like, if the blue vector we know is pointed at east 30 degrees south, and this is pointed 65 degrees, to the north of that, well, we take 30 of them away, that would get us back to east, and then we have 35.24 left to go towards north. So we're going to say this answer is relative to the wind velocity towards the air velocity. So our final answer is just going to be 558.45 kilometers per hour. Okay, and it is east 35.241 degrees north. And that is consistent with, what this says. This would be the counting it north towards east, but my number and this number add up to 90, so we know they're actually pointing to the same place. Okay, so again, really good question, tricky, but you try to get the hang of how to draw these. It all comes down to drawing it correctly, and draw this section especially nice and big so you can clearly tell which angle is which. Okay. Now, let's try another one. So there's just one more today, and then I'm gonna post a. Yeah, let me think about that. But you know what? There's the assignment today, so that's fine. You can just work on the assignment or the textbook. Okay, so last one here is just a canoeist wishes to cross a river that's 1 kilometer. The current flows 5 kilometers per hour south, and the canoeist can paddle 13 kilometers an hour in still water. At what angle to the bank must he head if he wishes to canoe directly across the river? Find the time it will take him to cross the river. Now, it's not totally clear. Well, yeah, no, I guess it is. Okay, so if the current's flowing south, then the river's going south, right? So let's draw it in this format first. And the first thing we're going to do is we're going to draw the, let's make vector B the current. So it says the current is 5, but I need to be able to fit 13, so I'm going to say it's 0.5. And the canoeist is going to be going at 1.3. Okay, so there you go. Now the current faces south, so I'm going to set it to a true bearing of 180. And the canoeist, we're trying to figure out so the canoeist can travel directly across the river. Of course, if the canoeist tries to head directly across the river, right, then he's not going to end up where he thinks. He's going to end up, down further south, right? So the question is asking us, how should we rotate this so that he ends up traveling, right, exactly the way he wants? Which would be something like this. So I'm thinking the answer is about 67.4, because now if he uses up some of his velocity to go into the current, then that will cancel what the current is doing, and he will be able to travel straight across. Now, of course, he's not going to travel straight across as fast as his regular speed. He can paddle 13, right? He's only going to travel across at 12 because some of his velocity is used up fighting the current. Okay? Now let's answer it the way we would here. So again, let's make a new sheet and see if I can learn from my mistakes. So his origin, let's say, is at 0, 0, and his destination is across the river. Let's just say 20, 0. I don't think it actually says how far the river. Well, it says it's 1 kilometer in width, but I don't want to. 1 kilometer is going to be too small to demonstrate what I want to show. So anyway, so here's the river. So let's quickly draw the river. So x less than 0, x greater than 20. We'll make these land, and 0 less than x less than 20 will be the river. Okay, so here he is. He's at point A. He wants to get across to point D. Oops. Okay. Now we know that the current, right? The current is traveling. Okay, that was confusing. Let's hide this for a sec. The current is traveling south. Okay, and we know the current is 5. So let's just bring B up a little bit so that it's actually, let's bring A down a little bit. Makes more sense. Okay, so there's the current there, and we'll move this over to be. Yeah, no, never mind. Okay, and then we know that he can choose the way he wants to travel. So this is what makes this question a bit different. This is the way he's going to travel, and we know that his resultant is going to be flat. So you see what makes this different, right? So okay, so what we're trying to do here is we're trying to get the way he should head out, right, correct, so that let's just redefine E as V plus W plus D, sorry. Okay, so how should he head out so that his resultant velocity, right, is sort of perfectly along, right, perfectly along the shore? Okay, so here's how you're going to solve this one. Again, you're going to draw a triangle. You know the triangle needs to look like this. We also know that the triangle needs to have the way this guy is traveling, right? He travels at 13. So let's draw what we know. Okay, so let me get rid of this circle. What do we know? We know that he travels at 13 kilometers per hour. Okay, that would be, in this case, it would be the hypotenuse of the triangle, right? Because this is the way he's headed. We know that over here is 5 kilometers per hour, and that is the current. And what we need to know is, and we know the bearing of his resultant. We know that the bearing of his resultant is 0. Okay, so that tells us that the resultant and the current have to meet at 90 degrees. So let's write 90 degrees. Okay, so the the resultant and the current have to meet at 90, and then all we need to do here is it's just a right triangle. We just need to work it out. So the question asks what angle to the bank he must head if he wishes to canoe directly across the river. So angle to the bank, let's just draw the bank again, would be the angle up here, right? This would be the angle he's making with the bank, not the angle he's making with, nothing. Remember, this is just water. So to get that angle, I'm going to get the angle inside first. So I'm going to do, let's just use our sine, because we know the opposite and we know the hypotenuse. We don't actually even need to get W yet. So 22.62 would go inside my triangle, right? It would go right down here, which means 90 minus 22.62, 67.38, would go, would go outside. So I'm going to give the answer. He needs to travel. He must travel at an angle of 67.38 degrees to the bank. Okay, and again, 67.4 is what I said here, but 38 is probably more accurate. Let's change it to bearing is 67 point. Right, and now it's pretty perfect within 2 decimals anyway. Okay, so he must travel at an angle of 67.38 relative to the bank. How long will it take him to cross the river? Now, okay, to do this, we need to remember that he actually moves relative to the ground according to his ground speed, or ground velocity. His ground velocity is 12 kilometers per hour directly east. Let's look at the picture again. Okay, his ground velocity is 12 kilometers per hour. That's this vector along the bottom, and it's directly east. How do I know it's 12? Is because this is a right triangle. 13 squared minus 5 squared is 100. Okay, yikes. 13 squared minus 5 squared is 144, and the square root of that 144 is, of course, 12. So that's where I'm getting 12 from, right? So he's traveling at 12 kilometers per hour east. The question is, how long will it take him to cross a river that's 1 kilometer long? Time equals distance divided by velocity. Okay, and therefore you just get a 1 kilometer divided by 12. One twelfth of an hour. So let's multiply that by 60, 5 minutes. Okay, you could leave it as 1/12 of an hour if you want, doesn't matter. Right? So it would take him 5 minutes to cross. Now, importantly, he does not cross the river at 13 kilometers per hour. He's paddling relative to the river at 13 kilometers per hour, but the river is moving. So he's only going to cross the river at his resultant, his ground velocity. That's 12. It's headed directly east. So the question is just how long does it take him to travel 1 kilometer east? If he's traveling at 12 kilometers per hour, the answer would be 1/12 of an hour, or 5 minutes. Okay, so try the assignment for today. Remember, it's not a test for Unit 6. It's going to be lumped in with Unit 7. So for now, just try the assignments and post any questions. Have a look at the study sheet that was posted as well. It's quite helpful.